Sea ice is frozen seawater, so it arises when seawater freezes, and then it's floating on the ocean until it melts. And when it melts, it flows back into the ocean. And we use radar satellites to observe the sea ice, so we have the radar properties of the sea ice that we can measure. So how the echo of the radar is transferred back to the satellite, this information we use to differentiate the sea ice.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring stories of resilience, hope, and scientific insight into climate change. If you haven't guessed already, today we're learning about sea ice. This episode of Down to Earth is brought to you by the Remote Sensing Environment Analysis and Climate Technologies, or REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society. The REACT Technical Committee is a collaborative and supportive venue for all scientists and engineers looking to exchange ideas and share knowledge that advances our efforts to tackle climate change. To learn more and be part of this incredible cutting-edge community, visit grss-ieee.org and select the REACT Technical Committee.
When new seawater freezes, usually it's a thin layer, a very thin layer, and this is for ships, hardly any resistant, hardly. And then when the freezing continues, it becomes thicker. And if ice flows are pushed together by winds and ocean currents, for instance, from different directions, then ice flows can be piled up on top of the other. And then a thick and uneven sea ice cover is formed. This is usually named pack ice.
This is Dr. Anja Frost, research scientist at the German Aerospace Center. Her work focuses on iceberg and sea ice monitoring using synthetic aperture radar.
Icebergs are not sea ice in this sense because it's sweetwater ice that is breaking off glaciers. So one of the main differences is that sea ice is forming by seawater, which is then turning into sweetwater ice because the brine solution is diffusing out, as opposed to icebergs, which is sweetwater ice in the first place and then just floating on the water.
And this is Dr. Sven Jacobsen. He's the head of the German Aerospace Center's Maritime Safety and Security Lab Bremen. Together, both Anja and Sven use their expertise to support ships traveling through the Arctic. Their research helps to optimize ship navigation, reduce emissions, and improve the technologies and processes for studying sea ice using remote sensing. So, it's my understanding that you both primarily use synthetic aperture radar to study sea ice. Tell us a bit about this and any other technology you use.
Yeah, so there are many sensors that are used to derive sea ice properties. There's SAR, which we are mainly doing, so synthetic aperture radar, but there's also altimeters to determine the ice thickness. There's passive microwave sensors that look at the microwave emission, and there's optical or hyperspectral sensors that have many optical bands where they are trying to derive properties of the sea ice. For instance, infrared channels to get the temperature. But mainly we are using SAR, so synthetic aperture radar, because it's very independent in terms of cloud coverage. It doesn't need any sunlight as opposed to optical sensors. So we can also operate in the polar night and get information during ice formation, which is not possible for these optical satellites. And we have a relatively high resolution of up to a couple of meters, usually in the modes there, sometimes also 30 meters, but it's still way higher resolved than for most optical or passive microwave sensors. So the SAR technique is, to put it in easy terms, more like an echo sounder. You send out an impulse in all directions and you pick up the return and look at the time delay between the sending and the receiving, and that determines your distance. And you look at the Doppler shift, the frequency shift of the signal, to determine the direction. With these two data, the delay plus the Doppler shift, you can find one pixel and contribute the return to this one pixel. If things are moving, they are displaced. So if I have a ship which is displaced with respect to the ship wakes, we can use this displacement to derive the ship velocity, and we can measure it and contribute a velocity to the ship afterwards.
And For those who have never seen a SAR image of sea ice, can you describe what it looks like?
Yeah, so first of all, if you have open water, the most radar response is reflected away from the satellite and we don't get an echo. So in this case, we display it black. If some echo is coming back to the satellite, we show it in grayish or white, depending on the strength of the echo. So how loud is it? So the louder, the whiter. So an iceberg is a good reflector. So we get a good response from an iceberg, and then icebergs look like white dots in a black background if it's floating in open water. Sea ice gives some response, so it's usually in grayish colors. You see the borders of flows or pressure, which is brighter, usually. So it depends on the sea ice properties.
Very interesting. And how long have we been able to study sea ice using satellites?
So I think we have Earth observation satellites since 4 decades, and especially radar satellites, to my knowledge. So since 4 decades, we have satellite imagery over sea ice and can study the sea ice.
Over 4 decades. Wow. I imagine the technology and in particular the resolution of the images has changed dramatically. So how do you handle this for time series?
Yeah, this is a tricky thing. So we always have to adapt. So for the 40 years coverage, this is not one satellite that is flying since 40 years. There are several satellites that have recorded for maybe 1 decade and then the next satellite. And in best case, we have an overlap so that we can adjust the satellite properties best to the same sea ice so that we can really compare it. But yeah, this is one of our main duties to make sure that we measure the correct stuff.
And do you also use ground truth data to
Yeah,
compare your
yeah,
satellites?
that's the core. Yeah.
However, the ground truth is very rare, as there are not many ships operating and not many sensors being deployed there. So,
And not many humans staying around and maybe telling us how the sea ice is there,
yeah,
especially for the central Arctic.
exactly.
There's nobody.
So that's the tricky part, I would say, because we need the ground truth to tweak and improve our methods, but it's not readily available as other sources. So sometimes we also have to take, let's say, ground truth, which is not technically ground truth. For instance, human operators that are very experienced in classifying ice types by eye on SAR images, we consider this to be ground truth, although no one was there actually looking at the ice in place and seeing whether this is true or not. So technically, this would also introduce some errors, of course, into our method. However, we hope that statistically it's still good enough.
And what can we do to improve our ground truth access?
Yeah, there's basically two things. One is more expeditions and maybe camera footage or so that we can also look at the ice ourselves. However, this is of course not really feasible in polar night conditions or these things, so it wouldn't work for any cases. But that would help, of course. And the other thing would be more satellites, because as Anja said, if you have time series or even the nature of the information or the quality of the information products can be improved if you have multiple sensors and you have, for instance, different angles to look at the ice or different sensor properties and fuse the sensor data. So the more satellites, the better for us to get a better data set on the basis of which we then derive the ice properties.
Well, speaking of fusing satellites, one of the projects that you recently worked on, Anja, was Ice Class 2. This project explored new techniques for generating sea ice information by combining data from different satellites, right?
Yeah, Ice Class 2 was a research project funded by the German ministry, and our partners were Drift and Noise, a company from Bremen, and Oasis from Hamburg, and in the subcontract iLab and König and Partner from Gießen am Ammersee, so southern Germany. And we together researched for using Sentinel-1 and Sentinel-3 data jointly. So Sentinel-1 is a SAR satellite, radar satellite, and Sentinel-3 is an optical satellite. And by using these different sensors, we wanted to improve the sea ice information that we can get, as both sensors are giving different information from the sea ice. So, and what we found out is that Sentinel-3 is very good in differentiating young ice in a finer way than we are able with radar, and also to differentiate open water. So not only saying this is all open water, but there was open water that is ready to freeze and open water that is far away from freezing. And this is also important information for some users. Radar, on the other hand, has a higher resolution and sees through clouds and darkness, where the optical images, it cannot see through clouds. So yeah, in the project, we use the data jointly. This was a research project, and we are not at the end of the research, even though we are at the end of the project.
In your view, what's the next step for improving our ability to study sea ice?
So for sea ice researchers using remote sensing data, there are three main ways that I actually see. So for improving the sea ice information that we retrieve from radar especially. So one is using different sensors like in Ice Class 2. One is using different frequencies, so still radar but on different frequency bands. And the third is using multi-temporal data, so using a time lapse to classify the sea ice in a better way.
That makes sense. Thanks, Anja. And Sven, in 2019, you participated in the largest polar expedition to date, Mosaic. This project improved our understanding of sea ice too. So tell us about this mission. What was the goal of this project and how has it contributed to our knowledge about sea ice?
Yeah, one of the main goals of the Mosaic expedition was to analyze the year-long Arctic drift. So there was a ship attached to an ice floe, and it would float across the North Pole over the year. And it gave us the opportunity to study the full seasonal cycle of the sea ice, but it was also intending to link processes across the scales, across the different size scales of this system. For instance, climate models, they have a pretty rough resolution, but they need processes that are small scale to be parametrized in the model. So to get a better glimpse of how these small scale processes need to be parameterized in a big scale model, this was one of the intentions.
And what did Mosaic teach us about sea ice that we didn't know?
So it gave a better estimate for these sub-grid scale processes, so they can be better put in climate models. And it gave us the opportunity to cross-validate different instruments. We have at our group a PhD thesis also dealing with combining ice-mounted scatterometers to the SAR data. So you have a sensor mounted directly on the ice, which measures similar things as compared to the SAR. So we can actually also look at, we have two different instruments and can cross-validate them. So that was a very good thing for us. Yeah.
Okay, let's bring all this talk about SAR, sea ice, and shipping routes together, because both of you primarily work on improving ship navigation through the Arctic. So, Anja, how have the results of Mosaic been useful to your work at the DLR Maritime Safety and Security Lab?
At the DLR Maritime Safety and Security Lab, one of the software processors we are developing is for automatic sea ice classification. And for this, the data from Mosaic with the cross-validations Sven mentioned were very helpful.
Yeah, for instance, we also have the first time we have overlapping results of the ice topography. So they had aerial campaigns where with airborne laser scanner, they had the ice topography mapped. And we have the first time we have the opportunity to compare this to the SAR data. As the topography, the inclination of the surface also influences the SAR return intensity. This is interesting. Also, the ice thickness is something that you get from the ice topography or the ice height. And this is also something we would like to get from the SAR. And this time we can look for correlations between the signals and find mechanisms that make it possible for us to determine the ice thickness later on.
Now, I understand that classifying sea ice, glaciers, or even icebergs could be a little challenging. So, if I'm not mistaken, you use machine learning for automatic classification of sea ice. Can you tell us a bit about how machine learning is helping to help create sea ice maps for use for ships or for anything else?
So what we are trying to mimic with these machine learning techniques is to have like an operator. The ice services, they work usually with an operator looking at the SAR images and classifying the image on the basis of their experience. They have looked at the evolution of the ice during the past weeks or so they are pretty sure what ice type there is. So there cannot be multi-year ice a week after there was no ice at all. So they know this. And what we try to do with the AI-based methods is to mimic their classification, but on the other hand, also to make their work easier. And the first step would be to segment the image so they can only click on a segment where they have similar ice characteristics and just label this. So this helps them improve their workflow so they can concentrate more on the single ice parts and look at it in more detail because they have their deadlines on a daily basis. They have to provide, for instance, the German ice service, they have to provide the ice charts at 14:00 in the afternoon. And if they have a lot of different ice types in a certain area, it makes it hard for them to do this in time. And if we provide them already segments or suggest classes, then this would help them. In the future, if these techniques are reliable, then it would generate automatic ice charts and they can be sent to the ship directly maybe. But I tend to have an ice service have an eye on this before being sent out because ships are taking their decisions based on the ice map. And it should be at least a human being involved in this procedure, to my mind.
Now, that will be a bit hard. This might be an obvious question, but why is it useful to have a real-time satellite sea ice data for ships? Why can't they just rely on their ship radar?
Because satellite images are larger in spatial coverage. So with the ship radar, you can see in a few kilometers radius around the ship. This is important for tactical navigation, so to surround, for example, flows that are drifting. But with the satellite image, we get, depending on the satellite you use and which mode you use, but it's at least 100 times 150 kilometers or 200 or 400 kilometer times 400. So you have a broader range and then you can already look for a route that might be useful for the ship.
Yeah, if I can add to this, if you, as Anja said, separate this into tactical and strategical navigation. The tactical is one where you look at the nearest neighborhood and like drive around a certain flow or so. And for the strategic planning, you would decide whether to go north or south of an island, where is the ice better suited, or look for predominant directions of open water channels. So you get an idea where to have the least resistance to your ship. Or like what we do, we also provide, or at least we're working on drift data, and you can see in this data where there's ice which is compressed or where ice parts are diverging. And of course, your resistance is lowest where the ice is diverging. So you would choose a course in non-compressed ice.
Okay, I know what you're thinking. What does trans-Arctic shipping have to do with climate change? And why does route planning matter? Also, how worried should we be about melting sea ice? We'll share the answers to these questions right after the break.
Are you passionate about protecting our planet and tackling the challenges posed by climate change? Do you want to be a part of a remote sensing community that brings together the brightest minds in environmental science and engineering? Then you need to check out the Remote Sensing Environments Analysis and Climate Technologies Technical Committee, or REACT-TC for short. Here on the REACT Technical Committee, we believe strongly that interdisciplinary collaboration is key to making a real difference in our world. That's why we bring together experts from various fields to exchange ideas, share knowledge, and advance the science that drives our understanding of the planet. Whether you're a scientist, engineer, or simply someone who cares deeply about the environment, the REACT Technical Committee of the IEEE Geoscience and Remote Sensing Society is a place for you. Together, we can make a difference, one discovery at a time. Visit grss-ieee.org and select the REACT Technical Committee to learn more.
Welcome back. Today we're speaking to two researchers with the German Aerospace Center. Dr. Anja Frost, research scientist, and Dr. Sven Jacobsen, head of the Maritime Safety and Security Lab Bremen. Both these researchers specialize in studying sea ice, and in particular, they help ships better navigate changes in Arctic sea ice flows. Now, before we jump back into the interview, I want to clarify why studying Arctic sea ice is so important for ship navigation and why maximizing ship navigation is important for climate change. So, sea ice in the Arctic can move very quickly. If the ice around a ship starts to converge, the ice can accumulate to form ridges. This can put a lot of pressure on a ship's hull, sometimes damaging larger ships, and sometimes lifting smaller vessels completely onto the ice. Ice ridges can also form walls that prevent ships from continuing forward on their path. Currently, most of the ships that navigate the Arctic waters operate using what's called heavy fuel oil. Heavy fuel oil is an extremely toxic, thick type of marine fuel that produces higher emissions of harmful pollutants and poses a massive risk to Arctic ecosystems in the event of a spill. While the Marine Environment Protection Committee of the UN's International Maritime Organization recently approved a ban on the use and transport of heavy fuel oil for ships in the Arctic, this ban will only come into effect as of July 1, 2024. With the ban's current exemptions and waivers in place, the complete ban is unlikely to take effect until mid-2029. In the interest of protecting this fragile ecosystem, particularly as melting sea ice both continues to make trans-Arctic navigation more attractive and sea ice formation more unpredictable, it's important to ensure ships can safely navigate these waters. To do that, scientists like Sven and Anja have to understand the ice properties and characteristics of ice covers so they can predict how sea ice is going to move. This is why, as you heard earlier, they differentiate between new ice, which is relatively thin and easier for ships to navigate, and older ice, which is much thicker. So how do researchers like Sven and Anja use this information to support ship navigation? Well, as Anja mentioned at the start of the episode, the various properties of sea ice show up differently in SAR imagery. Icebergs are good reflectors, so they appear white. Sea ice is less reflective and appears grayish. But when sea ice is accumulating and under pressure, like when it piles up, the ridges appear more white in the SAR imagery. As Sven explained, SAR imagery also allows them to see the displacement of sea ice, or rather, its movement. Because these scientists know how sea ice forms and what can cause it to pile into ridges and walls, they can watch the sea ice displacement happening and provide ships the navigational directions that help them avoid dangerous interactions with the sea ice. These directions also help reduce the amount of fuel required for their trans-Arctic journey and make their trip slightly more environmentally sustainable. Having satellite information in near real time is therefore pretty useful for ships navigating the Arctic, but it can also be useful when it comes to climate change. Let's learn how. So from a climate perspective now, how is this real-time sea ice data relevant, specifically as we experience climate change? Are we seeing impacts on shipping routes? Is it becoming more dangerous?
The key is to optimize the route. So this near real-time data is helpful to optimize the route. And that means in terms of CO2 emission, because if you have less resistance, you use less fuel. But it also in terms of safety, you wouldn't want any shipwrecks or shipwrecking in the sensitive ecosystem in the Arctic, for instance. So this helps ships navigate more efficiently and also more safely. That's the baseline, I would say. Also, our data contributes to this system understanding of the climate, so climate system understanding via improving the models and these things. But we can also use our data in mitigation and adaptation to climate change. For instance, if we leave the ice topic a bit and look in sea state, we can identify hotspots for coastal protection, where there's a lot of erosion, where dikes are exposed to storm events. And we then can concentrate countermeasures to improve the efficiency of coastal protection. And in terms of mitigation, this route optimization is a means to mitigate these climate change effects because we are reducing the emissions and therefore saving fuel and reducing the climate effect of ships.
Mm-hmm. Mm-hmm. So when we first started our interview today, you both mentioned that wind and ocean waves play a role in the formation and movement of sea ice. Can you explain how do we account for these variables in the ice information you generate for ships?
Yeah, I don't think it's directly affecting the ships, but for climate models, like waves break up the ice, and so it leads to faster melting of the ice. So if we have stronger storm events, for instance, it would break up the ice quicker, and then the melting would be accelerated. If you look at the ice and you see how far these waves penetrate into the ice, it gives you also hints on the ice thickness. So there's a lot of information that you can get from combining sea state information plus ice information, at least in the marginal ice zone, where you have a solid ice surface. Yeah, it's the same for wind. So we also can derive wind information from SAR, and can even see wind on larger areas of open sea that is surrounded by sea ice. And this helps you also to quantify the forcing on the ice and analyze the ice drift and get models to predict the ice drift better on the basis of wind and sea state data.
And how are ocean currents playing a role in sea ice formation and melt?
For the drift, of course, they play a role, but they're at least equally wind and sea state, or wind mainly, are also contributing to the ice drift. For the ice formation, that's a tricky question because in the Arctic, the ice is forming, let's say, in columns. Like first the top freezes, the very surface, but then it is more or less growing deeper and deeper. Whereas in the Antarctic, where you have a land mass surrounded by an open ocean and much more currents and sea states interacting with the ice. Below the ice, there is calm conditions for the ice to grow. So the mechanism of ice growth is influenced by the presence of currents and sea state. And therefore, that's basically one of the major differences between Arctic and Antarctic sea ice.
Though the wind has the strongest influence to the sea ice drift,
Yeah.
so not the currents. For icebergs, it's the opposite way, as icebergs are from land origin, as we said in the beginning, and it has another depth, so it's deeper. And so icebergs are drifted by ocean currents and sea ice mainly by winds.
That's really interesting. We hear a lot about the urgency of sea ice and glacier melt. Why is sea ice melt an issue for the Earth?
If the sea ice melts, the whole Gulf Stream mechanism is based on warm water cooling down and then dropping to greater depth. And then basically it's a pump which is not working if there's not the temperature difference between warm Gulf of Mexico and cold Arctic weather. So, the whole climate will change.
Sorry, are you saying that if the sea ice melts, then it's going to change the Gulf Stream?
Again, I'm not a climatologist, but like what I read from papers and what I pick up at conferences is that you have basically a thermally driven motor where there's warm water going from the Gulf of Mexico, passing by Europe, and then going to the North Atlantic. And there it is gradually cooled down. And then when it's getting very cold in the Arctic waters, it's dropping to the ocean bottom. And then it's flowing backwards to the Gulf of Mexico, at least in this area, or to southern waters again. And then this whole pump of like heating up, going to the surface and then dropping to the lower water levels. This is all driven by the temperature difference. So this is how it works, but it only works if you have a temperature difference. If the temperature difference is getting smaller, then this can also stop the whole process. And that would be catastrophic. So we don't look at this data because this is basically sea surface temperature and probably also probing the lower parts of the ocean. And we, with our remote sensing satellite, or with the SAR satellite, I have to say, we are not looking into this. But we are looking into monitoring of storms and other phenomena that are said to be related to climate change and maybe even to changes in ocean currents and these things. So we actually look into wave heights in storms, and in the future with long time series we may be able to determine, okay, there's the energy in the waves has increased by such and such percentage over the last 20 years or so. But we're not there yet. We can now determine sea state properties very well since, let's say, a couple of years from SAR satellites, and we have global data on this, but now we need the long time series to actually pinpoint down this small or gradual effect.
To reinforce Sven's information about the Gulf Stream here, this year NASA published an article on this very topic, reporting that as the ocean continues to warm and land ice melts, ocean circulation could be impacted. So some basics on ocean circulation. Ocean circulation is responsible for transporting heat from the equator to the north and south poles through currents. Winds and the Earth's rotation are partly responsible for generating ocean currents that enable this circulation. Ocean density also plays a role. Cold water and salty water are both denser than warm and fresh water. So, cold salty water sinks and is replaced by warm water. This cycle is especially obvious in the North Atlantic. There, the surface water evaporates, cooling the water temperature. In addition, the cold temperatures support sea ice formation, which, as Anja and Sven explained earlier, causes the separation of fresh water from salt, because salt doesn't freeze. This makes the surface water saltier. Once it's dense enough, it sinks and is replaced by warmer, less dense water from the Gulf Stream. If temperatures continue to increase, Arctic waters will continue to get warmer. If there's not enough cold, dense water to sink, the circulation in the Atlantic Ocean will weaken, causing major changes to the climate globally. Now, don't panic. The International Panel on Climate Change has reported that the Atlantic circulation is unlikely to stop or collapse before the year 2100. But it does point to the importance of the work both Sven and Anja are doing. By studying sea ice, they are helping to track a major contributor to our ocean currents. And as the sea ice melts, their work is expanding to include sea states because trans-Arctic ships will need to navigate increasingly storm-impacted waters. So this is how shipping routes, sea ice, and climate change all tie together. So our oceans are definitely affected by climate change and the rise in temperatures. And this, of course, affects how sea ice is formed. But what if all sea ice melts? Then we're dealing with more storms and coastal erosion, so not exactly a positive circumstance. So what keeps you positive about your work in light of climate change?
I think overall, the oceans that cover by far the largest area of our planet, there's very little understanding as compared to the importance for us. So if we help provide data to understand the system better and to improve models and to get a better view on this and even promote the existence of the importance of this system, it already helps to generate public awareness for this topic. So if we help promote and understand the importance of this system, that already helps. The other thing is that at least we can also work in mitigation and adaptation to this phenomena. And for instance, improve coastal protection measures and these things. I bought a house which is technically, I guess, 7 meters above sea level. So I have a personal interest that it's not that sea level rise is not getting out of hand. And I'm still optimistic, although I have to admit we don't know the system well enough to actually say whether it's already too late or not.
Anja?
So until 2050, ships have to reduce the emissions to 50% already. And so those who are building ships are already thinking to build ships that has less emissions. So they will maybe go down to zero emission. And this is one thing that keeps me positive. And the other thing is, by observing the sea ice from space and reporting how it is shrinking, it hopefully reaches the people and the politicians to build up rules and laws that preserve the sea ice that we have.
Well, that's all for this episode of Down to Earth. Want to learn more about Anja and Sven's work?
People can follow our work at DLR from the DLR webpage. There are also social channels, or of course look at research papers.
Rate and follow us on Spotify and Apple Podcasts, and tell us what topics would interest you for future episodes. And send some love to our sponsors at IEEE_GRSS on Twitter and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Irina Hansek of ETH Zurich and the German Aerospace Center for her support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.